This is section 10.3, and we're going to continue to work with polar coordinates, but now we're going to do some calculus with functions in polar coordinates. We'll start with sort of that age-old question, right? The slopes of the tangent lines. We've done them in rectangular coordinates back in Calc 1. We did them with parametric equations in 10.1 this semester, and now we'll do them with polar graphs. So let's suppose that we want to know the slope of the tangent line to the graph of the polar function, r equals f of theta. We always know the slope of a tangent line is dy dx. We just have to come up with an expression for dy dx in polar coordinates. Keep in mind, when working with polar coordinates, we always have the relationships between x and y and r and theta. X equals r cosine theta, and y equals r sine theta. If we're working with a particular polar graph, then we have r equals f of theta. So we can actually just substitute f of theta for the r's in those equations. So I could write my x as f of theta cos theta, and the y could be f of theta sine theta. When we do that, notice we've now expressed both x and y in terms of a third variable theta, so this counts as a parameterization. These are now parametric equations using parameter theta. That's actually a really good thing for us because we already know how to find dy dx with parametric equations, right? So from the study of parametric equations, dy dx. With parametric, we did dy dt over dx dt. Now, because our variable, our parameter is theta, we'll do dy d theta over dx d theta. Again, remember, if you just imagined dividing by doing a reciprocal and multiply, the d thetas would cancel out, and you'd have dy dx. All right, well, let's work on this a bit more. To do dy d theta, look at y. Y is a product of f of theta times sine theta. And similarly, when I go to do dx d theta, x is a product, f of theta times cosine theta. So each of these is going to require that we have to use a product rule. Remember? U times v prime is uv prime plus vu prime, right? Would be one way of saying it. So let's do that. dy d theta on top. I would have the first times the derivative of the second. So f of theta times the derivative of sine theta, cos theta, plus the second sine theta times the derivative of the first, f prime of theta. Same idea on the bottom for dx d theta. There's x. Here's the product form. So when I go to do dx d theta, first times the derivative of the second would be f of theta times a negative sine theta. I'm going to pull the negative in front. Plus, second times the derivative of the first, cos theta times f prime of theta. Typically, you'll see this written like this. For whatever reason, we tend to write the derivative terms first. So I usually write the top as f prime of theta sine theta plus f of theta cos theta. And the bottom as f prime of theta cos theta minus f of theta sine theta. And I'm sorry that you couldn't see that last bit I wrote, but there it is. Just reordering the terms. Right? So that is typically what we'll use as sort of our, it's not really a definition because we proved it, but our method for calculating dy dx, the slope of the tangent line, if we're given a function in parametric form. That is given to you again, kind of formally, in the box at the top of the next page. So once again, if we've got r equals f of theta, a curve in polar coordinates, the slope of the tangent line to the curve can be calculated using this derivative, and of course we'll always have to plug in the appropriate theta to get the actual numerical value of the slope. So in this first example, I'd like the slope of the tangent line to the curve r equals 8 sine theta at the point 4, pi sixths. Slope, no matter what coordinate system we're using, is always dy dx. In this case, I'm going to be using this definition of dy dx, or this formula for dy dx, because we are in polar coordinates. Here's what I use for f of theta, since that's what r equals. And so we'll have f prime of theta would be 8 cosine theta times the sine theta here plus f of theta, 8 sine theta times cosine theta over f prime of theta, 8 cosine theta times that cosine theta minus f of theta, 8 sine theta times another sine theta. Whew, all right, what do we got? Top is actually 16 sine theta cos theta. Bottom would be 8 cos squared theta minus 8 sine squared theta. All right. Ultimately, I'm going to have to plug in the theta value that I have here, which is the pi sixths. And certainly I could plug this in right now if I really wanted to, but it's a little bit of a mess. I'm going to go ahead and play around with the trig a little bit. If you're not wild about that, yes, you really can plug in the pi sixths right now. I'm going to do a little simplifying. A little trig is always good for the soul, right? I'm going to actually start out with an algebraic simplification. I'm just going to divide by 8, top and bottom. So I have 2 sine theta cos theta over cos squared theta minus sine squared theta when I divide out that 8. And I really like that because those are 2 trig identities that I recognize. They're both double angle identities. The numerator is just sine 2 theta, and the denominator is just cos 2 theta. So I've got sine 2 theta over cos 2 theta. Otherwise known as tangent 2 theta, so I really could even simplify it more to write on paper, but Since I'm going to look stuff up on my unit circle, I'm going to leave it as sine and cosine because that's what I can look up easily off my unit circle. All right, so we're plugging in this theta equals pi sixths. So I'd have the sine of 2 pi over 6 over the cosine of 2 pi over 6. Two pi over 6 is pi over 3. And for pi over 3, sine is square root 3 over 2, and cosine is 1/2. If I either invert and multiply or multiply top and bottom by 2, right, form a 1, I cancel out those 2's. And I just get the square root of 3 over 1, or the square root of 3. So that's the slope of the tangent line at the point we're talking about. Right? This function is actually one that we talked a little bit about graphing at the end of 10.2. If you remember, or if you can look it up, or if you can use a calculator, right? The graph of r equals 8 sine theta is just a circle. It's centered on the y-axis with a diameter of 8. So it basically looks like that. The point that we were interested in, the point 4 comma pi over 6, at an angle of pi sixths, 30 degrees, right? We'd be kind of over here, 30 degrees, maybe about a third roughly here. That might be approximately the point 4 comma pi 6. I'm just trying to estimate about a 30-degree angle there. And what we're saying is that if we were to sketch the tangent line at that point, the slope of that tangent line is the square root of 3. It definitely seems reasonable. It's absolutely a positive slope. Looks like it's more than the diagonal, more than a slope of 1. Slope of close to 2, right? That's about 1.7 something. Seems reasonable for that answer. All right. Next example. I'd like to find the slopes of the tangent line, or tangent lines really, to the graph r equals 2 sine 3 theta at the tips of the petals. It's a giveaway when I say the tips of the petals, that's a rose curve, right? And in fact, with an odd multiplier in here, this is a rose curve with 3 petals, and the length of each petal is 2. We'll graph this at the end. Let's go ahead and find the slopes first, and then we'll graph it and kind of see if we can make sense of it. So, the slope, always dy dx, and since our formula is on the other page, I'm going to rewrite it for us here. It's f prime of theta sine theta plus f of theta cos theta over f prime of theta cos theta minus f of theta sine theta. In this case, here's our f of theta. It's what r equals. And so when I do my derivative, f prime of theta is going to be 2 cosine 3 theta, and chain rule times 3 times the sine theta plus f of theta, 2 sine 3 theta times cosine theta over f prime again, 2 cos 3 theta times 3 from the chain rule times cos theta minus f of theta, 2 sine 3 theta, sine theta. All right, not a whole heck of a lot I can do with this. This time, because I've got different arguments, I don't have things that go together quite as well. What I can do, it looks like I could probably divide a 2 out of every term, so just to keep things as small as possible, I'm going to divide by 2 over 2 as I make the minor simplifications here. So that's going to get rid of the 2 here, and I'll have 3 sine theta cos 3 theta plus, again I'm dividing out that 2, so I would just have sine 3 theta cos theta. On the bottom, divide out the 2, 3 cos 3 theta cos theta minus, divide out the 2, sine 3 theta sine theta. All right, I don't think any trig identities are going to save me very well there. So I think I'm going to leave it like that. I'm ready to plug in the thetas. But this time I wasn't given the theta. Wasn't quite that convenient. So I need to figure out the theta values at the tips of the petals. So, we already know it's a rose curve, 3 petals of length 2. In order to get a really good picture, of course, we can always use the calculator to help us graph. And I am in polar mode. So I'm just going to go ahead and do 2 sine 3 theta. And I'm going from 0 to 2 pi. I think I only actually need to go to 0 to 1 pi for this one. And everything else looks okay. Oh, no it doesn't. Sorry, my window was off. Let's do the zoom square thing. Well, that was weird. It's actually all right. We can see it. Right? So let's see. 1 petal's in the first quadrant. 1 petal's in the second quadrant. And the third petal goes around the negative y-axis, like so. Okay. I need the theta values here, here, and here. Now keep in mind, this equation is r is equal to 2 sine 3 theta. The trick here is to remember that the petals have length 2. Right here, that length, that r value is 2. Again here, that r value is 2, and here, that r value is 2. So if I substitute the 2 in for the r, 2 is equal to 2 sine 3 theta, and solve that equation for theta, it should give me the theta values that I need to plug in here, specifically the theta values at the tips of the petals. Dividing out the 2, 1 is equal to sine 3 theta, and so the inverse sine of 1 would equal 3 theta. And so I need to know what angle or angles have a sine of 1. And notice I'm going to need 3 of them. 1, 2, 3. So I'm going to notice here, sine is equal to 1 up here at pi over 2. That's the only place on this whole unit circle where the sine is equal to 1. So I'm going to say 3 theta equals pi over 2. To get 1 a second time, to get to the second pedal, what I'd have to do is I'd have to take this pi over 2 and then go all the way around to it again. So pi over 2 plus 2 pi. Or I could go around twice more, and I'd have 3 theta equals pi over 2 plus 4 pi. Let's see if I can squeeze that in there. Okay, that's just going around the circle multiple times. I know I need 3 answers because I got 3 places on my rose curve where the length of the petals is 2. Dividing by 3, this one would give me theta equals pi over 6. Here, let's see, that would be 4 pi over 2 plus 1 pi over 2 would be 5 pi over 2. And dividing by 3, theta would be 5 pi over 6. And finally on this last one, let's see, that would be 8 halves. 8 plus 1 would be 9 pi over 2. And again, dividing by 3, theta would be 9 pi over 6, or in lowest terms, 3 pi over 2. Whew, all right. So, I kind of think this makes sense. My picture's not perfect, but it's not terrible. It looks to me like our first theta value, pi over 6, would be right here. That's a first quadrant angle. That's in the first quadrant. Second one would be theta is 5 pi over 6. 5 pi over 6 is a second quadrant angle. So that's also okay. And then the 3 pi over 2 is the one right down here on the negative y-axis. Also looks good. So I think we did it. All right. Now I need the slopes at each of those points. So for each of these theta values, let's calculate dy dx using, of course, this beautiful formula that we came up with up here. Now that's not going to be a lot of fun to plug in my 3 theta values. So what I actually did here is in my function mode, I just put that whole thing into my y1. I'm using x's now instead of thetas, but the variable doesn't really matter, right? And I've got that whole thing in here. So what we're going to do is we're going to go to a table. And my first theta value was pi over 6. If I go ahead and put that into my table, I get negative 1.73. My next theta value is 5 pi over 6. And the slope that I get is positive 1.732. And then my last theta value was 3 pi over 2. And let's see, that's an exponent of negative 13. 3 times 10 to the negative 13th looks like round off error to me. I think that's 0. All right, let's see if those make sense. At pi/6, my tangent line would look like that. It would definitely have a negative slope, just like we got. And at 5 pi/6, my tangent line would look like this, and it would have a positive slope. With the symmetry of this rose curve, it makes sense that those slopes would have the same value, just one positive and one negative. So I'm pretty happy with those results. At 3 pi over 2, we certainly have a horizontal tangent line, and that's that slope of 0. So everything seems to be working out really well here. These are our slopes, and we're all set. Okay. One more example of using the derivative as an interpretation of slope. I'd like to find the points here in example 3 at which the curve r equals 2 plus 2 sine theta has vertical and horizontal tangent lines. If you remember, this thing's a cardioid. We're going to graph it later on just to see it, but that's a cardioid. Because the a and the b values are equal. And I want to know where the tangent lines are vertical and horizontal. Vertical, the slope or derivative, is going to be undefined. Vertical lines have an undefined slope. And horizontal, the slope or derivative is going to have to equal 0. So if I can find an expression for dy dx, which we can, we'll figure out where that's undefined and where it's 0. So here we go. Again, the slope dy dx, using our slope formula for polar functions. And again, I'm just going to quickly write it down here because it's on another page. This time our f of theta is the 2 plus 2 sine theta. So f prime would be, that'll be 0, and that'll become a 2 cosine theta times the sine theta plus f of theta, 2 plus 2 sine theta, times cosine theta. Denominator, f prime, again, is 2 cosine theta times cosine theta minus f, 2 plus 2 sine theta times sine theta. Let's simplify that a little bit here. We've got, let's see, let's write it out. 2 cos theta sine theta. Distributing here, I'd have a plus 2 cos theta and a plus 2 sine theta cos theta. On the bottom, we've got 2 cos squared theta. Distributing both the negative sign and the sine, I would have a negative 2 sine theta and a negative 2 sine squared theta. So on top, you know what, actually let's, as we go here, I'm noticing everything's got a 2 as a coefficient. Let's get rid of that. Let's divide by 2 over 2. Keep things as small as we can. I would have, once all those 2's are gone, then I'm going to have sine theta cos theta plus sine theta cos theta. So combining those will give me a 2 sine theta cos theta. plus cos theta. And at the bottom, we got cos squared theta minus sine squared theta minus sine theta. All right, that's not bad. I'm going to go ahead and leave it like that. And once we figure out the theta values we want, we'll go ahead and we can use that to go from. So what have we got here? I wanted to know where the slope was 0 or where it was undefined. So horizontal tangent lines, m equals 0. We know that a fraction is 0 when its numerator is 0. So I would have to say 2 sine theta cos theta plus cos theta equals 0. The numerator of the fraction is 0. And then vertical, slope is undefined. Of course, a fraction is undefined when its denominator is 0. All right, we got some trig equations to solve. Pulling back all your trigonometry skills here. First one's not too bad. I can factor out a cos theta. And so either cos theta equals 0 or 2 sine theta plus 1 equals 0. See, cosine of theta equals 0, and I'm only going to go from 0 to 2 pi here, because I know that this whole graph gets swept out from 0 to 2 pi. So on the interval from 0 to 2 pi, cos theta equals 0 here at pi halves, and again here at 3 pi halves. This one becomes sine theta equals -1/2. And let's see, that's going to happen right here at 7 pi over 6, and again over here at 11 pi over 6. All right, let's keep that in mind. And we're going to go to the verticals. We want to know where this is 0. It's the denominator of the fraction, so it makes the slope undefined. And this one's going to be a little bit more challenging to work with. We've got both sines and cosines of the equation, but we can't factor out anything right now. So what I'm going to do is I'm going to use the technique of getting all one type of trig function. I'm actually going to replace the cosine squared with 1 minus sine squared. Okay. I'm really just building off of this identity. Right here you can see cosine squared would be 1 minus sine squared. And then I'll just write out the rest of it. And now that I've got all one type of trig function, it's a lot easier to work with. So let's see here. I would have -2 sine. You know what? I'm actually going to bring everything over to the other side because I'd rather have a positive on my squared term. So I'm going to ultimately end up with 0 over here. That'll become a +2 sine squared theta. And that'll go over as a plus sine theta. And that'll go over as a -1. And I'm hoping I can factor that. Let's do a little trial and error here. 2 sine squared theta, going to have to be 2 sine theta times 1 sine theta. This negative 1, going to have to be 1 times 1. One of these is a plus and one's a minus, and I just have to figure out which is which. And let's see here. I need to get a positive sine theta in the middle. So I think if I go with plus here and minus there, that's a 2 sine theta minus 1 sine theta is 1 sine theta. So we got it. All right. If 2 sine theta minus 1 is 0, sine theta would be 1/2. And if sine theta plus 1 is 0, then sine theta is negative 1. Sine theta equals 1/2. There and there. Pi sixths and 5 pi sixths. Oops. Jumping the gun here. Sine theta equals negative 1. Just right there at 3 pi over 2. All right, I think we pretty much have things close to answered here. We're going to go ahead and talk about these in just a moment, but there's one issue I want to point out. Right now, the way this looks, I have a horizontal tangent line at 4 places, and I've got a vertical tangent line at 3 places. But did you notice one of those places is the same? That's a little weird. 3 pi over 2 came out of both solutions. That's a problem. We cannot have a point with both a horizontal and a vertical tangent line. So let's think about where that came from. Remember, this came from setting the numerator equal to 0, and this one came from setting the denominator equal to 0. So since 3 pi over 2 came out of both of those, that's actually a 0 over 0 case. It's that indeterminate form. And so it's actually not going to be either horizontal or vertical. So what I'm going to do is I'm going to get rid of those. Just make myself a little note. At theta equal 3 pi over 2, the slope turns out to be 0 over 0. It's an indeterminate form. What I'll do actually is I'm going to use the graph to kind of help me see what's happening there. But I think what we're going to discover is we don't have either a horizontal or a vertical tangent line at that point. But we'll look at the graph to see it. All right, so let's give this a shot. I'm going to, just for ease as I look at my graph, I'm going to make myself a little chart here. I'm going to trace on my graph to see these. So for each of these theta values, as I trace, the calculator, of course, is going to give me not pi over 2 or pi over 6, but it's going to give me decimal values. So let me just real quick convert to decimal form. And then I'll make a list of what kind of tangent line I have at each point. So going from smallest to largest, the smallest is pi over 6. Decimal value is about 0.52. And at pi over 6, that was in my vertical tangent solution. Next biggest value of these would be pi over 2. On the calculator, that's going to look like about 1.57. And pi over 2 came out of the horizontal tangent line column. Let's see, I think the next one's going to be the 5 pi over 6, next biggest. Just trying to go in order here. That's going to look like about 2.62 on my calculator. And that one was over here. That was a solution for the vertical tangents. And the next one would be 7 pi over 6. It's going to look like about 3.67 on my calculator. And that was here in the horizontal column. And then finally at 11 pi over 6. Decimal form about 5.76. And that one was also in the horizontal column. All right, let's take a look. Oh, I'm back in function mode. Sorry, let's go to polar mode. And I wanted to look at the function 2 plus 2 sine theta. And we should be seeing a cardioid. Let's take a look. On the window, we do need to go 0 to 2 pi to get this to graph. And let's see, my step size is probably fine. -4 to 4. And let's do the y's also, -4 to 4. All right, there we go. There's our cardioid. Not bad. And what I'm going to do is I'm going to trace it. And we're going to see if at these points it seems reasonable that we've got the type of tangent line that we discovered, or we think we discovered. So I'm going to trace. And notice that in addition to the x and the y, it also gives me the theta here. So here we go. First interesting point should be at a theta of about 0.52. There it is. Theta's 0.52. And notice right over here, it's very reasonable that we would have a vertical tangent line. Next interesting point is pi over 2, 1.57. Pi over 2 should be right at the top. And of course, it does look like that's going to be a horizontal tangent. Let's just verify. Oops, went past it. There we go. Theta is 1.57, and certainly at the top there. Horizontal tangent line seems reasonable. Next interesting one, 2.62. There we go, about 2.62. Again, very reasonable that we'd have a vertical tangent line there. 3.67. There we go. Right down here, horizontal tangent line again. Notice here at the middle, 3 pi over 2. That was the weird point, right? That was the one we kind of threw out. And notice we've got that sharp point there. As we learned in Calc 1, sharp points have undefined derivatives simply because coming in from the left and the right, they don't agree. So the fact that we threw out the 3 pi over 2 is very reasonable. That sharp point would definitely have an undefined derivative. All right, the last one, 5.76, right about there. Again, does look like a horizontal tangent. So I think all of these theta values are the correct values for the vertical and horizontal tangents. All right, that brings us to the end of the derivatives section of the calculus. We'll finish this section in the next part, or the next video, with the integrals portion.